All right, you guys, we are starting our last unit, our last new material that we're going to cover for this year. Your last bit of information that you need to understand for online learning to make sure that you understand what you need to know for the test for Missouri Baptist. So we're looking at chemical bonding and molecular structure. So this video is just going to be like the brief introduction, talking about bonding, what you need to know, and then we're going to actually move on in the last couple of videos that I do where you're going to actually be drawing structures. So I'm only going to be using this packet of notes for this part right here. For some reason, my notes are not transferring over correctly. Some of the stuff is not coming into this program that I'm using correctly. So I'm just using it for this part, and then I'm kind of breaking down the other pieces. So I am going to have some new notes that we're looking at to kind of just isolate exactly what I need you to know. But to start this whole thing out, we're just talking about bonding. So a chemical bond, and I kind of describe it up here. Oh, I'm not using a pen. Let's start that over. So we're talking about attractive forces. So things that hold elements together to make bonds. And what you need to understand about all of this is most of the things that we have in the world around us are not just elements. And they kind of say that down here. We're not just talking about elements. They're compounds. So it means that it's easier for them to be bound. It takes less energy for them to be in a compound than to be just in elemental form. So something that is a misconception for some people in chemistry is to understand that it takes energy to break a bond. So it's going to require some energy to break a bond, but energy is released when a bond is formed. So it requires energy to break a bond, and here's the definition of bond energy. So it's just the energy required to break a bond. So kind of going back to a previous science class that you have learned about ionic and covalent bonds. This Coulomb's law here, there's not much I need you to know about that. You're not going to be doing any calculations with that, so I probably wouldn't worry about that. So ionic bonds, what you need to understand about them is they are between, and I'm going to kind of draw an arrow over here, we're talking about elements with a metal and a nonmetal. One element actually gives up the electron to another element, and it forms a very strong bond. This is like salt. Salt has a very, very high boiling point, so it's a strong bond. And then we've gotten that example would be NaCl. That's the formula for salt. So I have a metal and a nonmetal. Whereas a covalent bond, these are where the electrons are shared. So that's because they are nonmetals and nonmetals. So maybe like Cl2. So what you learned in your physical science class was to say, okay, sodium has 1 valence, chlorine has 7 valence. So this sodium will transfer that electron there. Now, if you were listening carefully, I specifically said valence electrons. Doesn't matter what the total amount of electrons are. It's just what's going on with their valence electrons, and that's talked about down here. And then chlorine, Cl2, would be 2 chlorine atoms bonded. So we're talking about they each have 7 valence. They will share 2 electrons right there. So they form what's called a covalent bond because they're both nonmetals and they're sharing electrons. Whereas the other one, sodium, was actually giving up the electron to chlorine. So again, it specifically is talking about their valence electrons, and what I showed you was called a Lewis dot structure. So we're going to get into that more. You're going to learn a new way to draw these structures in this class. So that's why I'm going to kind of create a video to kind of go through that. But down here, when they start talking about chemical bond formation, so there's a couple of different levels of what happens when atoms go together. So there are 2 like bad things that they say. Obviously, when 2 atoms go together, the electrons are going to repel each other. Kind of like when you try to take 2 magnets and push them together on the same side. They won't go together. So there's going to be some repulsion between the electrons. There's going to be a proton-proton repulsion. But what happens to make them form that bond is you do have that proton-electron attraction. And if that attraction is enough, then they are able to kind of go together to form that bond. If it's going to be at a lower energy state, they're able to form that bond. So we do talk about van der Waals forces, but I'm not really going to touch on them. This will come in if you guys move on in chemistry, and I don't really want to go through it too much right now because I don't want to confuse you. So I'm going to kind of stop on this page. That's all I really kind of need you to understand about this page. All right, so next page. So level 2, we're talking about the orbital theory. So what's going on? What happens when atoms actually go together, because we've looked at electron configurations. So if one element has some electrons in an s orbital and one has some in a p orbital, and they combined, they form what we call a bond orbital. So they kind of, what you want to think about it is they mesh together. Those two orbitals kind of go together and squish together and make what we call a bond orbital. So you do have to understand also like what's going on with the bond orbital and then some lone pair orbitals. So that structure that I drew earlier, and I'm going to kind of draw it maybe over here. So when I had that chlorine atom, you need to start understanding what I mean by lone pairs. So the lone pairs are these dots that I'm showing. So they are sharing a bond. They are sharing those two electrons, but they have lone pairs. And there can also be lone pair orbitals. This we're just kind of touching on. I don't need you to understand a lot about this. So again, they kind of review here ionic and covalent bonds. Again, ionic bonds, extremely strong. Those elements are going to be really hard to pull apart. They have really high melting and boiling points because it's a strong bond. Whereas covalent bonds, not as strong. Now, for covalent, there are two types. There's a polar bond and there's a nonpolar bond. So a nonpolar bond would be something when we talk about like if two hydrogen atoms go together. So think of it as a tug of war game. Two hydrogen atoms are the same strength. So they're going to tie in that tug of war. No atom is going to win. So they form what's a nonpolar bond where they're just sharing electrons equally. But then if I have a bond, say with hydrogen and fluorine, if you look down here, we covered this topic last chapter, but it kind of comes back. It's actually covered in chapter 8, but I wanted to cover it with the trends. So we've covered the trends. We know, or you should know, that the electronegativity increases as you go across a row. So fluorine, highest electronegativity value at 4. And then francium, lowest electronegativity value at 0.7. So if fluorine is in a bond with hydrogen right here, there's not going to be an equal pull. One of them is at 4, one of them is at 2.1. Hydrogen is way stronger than, or fluorine is way stronger than hydrogen. So in a sense, you're going to see these symbols kind of drawn. That S minus means, and this S plus, that just means slightly negative. Fluorine is carrying a slightly negative charge because it's going to pull on that electron more than hydrogen is able to hold on to it. So in a sense, hydrogen kind of loses the electron to fluorine, but they're still sharing them. It's still not considered an ionic bond. So what you have to be able to do with this is you have to be able to kind of use this table, and it's not put together very good down here. You have to determine whether something is an ionic bond. If it's ionic, it has an electronegativity difference between the two elements greater than 1.67. And it's covalent, meaning polar covalent, if it has an electronegativity less than 1.67, but it's got to be, if you look at this last one right here, it's got to be greater than 0.4, because anything less than 0.4 is going to have an electronegativity difference is nonpolar, anything that's less than 0.4. So I'm going to do a couple of practice problems with you. So say we look at BH3. So it really doesn't matter that there's 3 hydrogen atoms. I'm just really looking at boron and hydrogen together. So if you circle them, here's boron's value, and I've already circled hydrogen up there. It's 2.1. The difference between those two is 0.1. So just take the larger number minus the smaller number. Well, if you look down here at this table, anything that's less than 0.4 is considered to be nonpolar. So you would identify that as a nonpolar bond. So another example would be like, I'm going to use a different color. Let's use green. So if you have NH3, well, again, H is circled, N is 3. So we've got 3 and we've got 2.1. So 3 minus 2.1, that difference is 0.9. Well, now if you go back over and look at this table, it's greater than 0.4, but it's less than 1.67. So that falls right in that middle category. This is going to be considered a polar, or sometimes they just call it covalent. I usually write polar covalent just to kind of clarify. And my last example would be MgCl2. Okay, so Mg is right here. It's 1.2. Cl is over here. It's 3. So 3 minus 1.2, that's a huge difference. That difference is 1.8. So that difference is greater than 1.67. So you would identify that as an ionic bond. So that's kind of how you go about figuring out, how do I identify these? What do I look at to figure this out? So as you can see at the bottom of this page, my practice problem kind of got jumbled all around trying to move it up into this program. So I'm just going to kind of work this one with you guys on the next page in an open spot. It'll be on the next page for you. Your notes are put together fine. Okay, so my problem was up there. I'm going to go ahead and work it down here at the bottom. We've already kind of covered this. So I already talked about whether something's polar, nonpolar, or ionic. So we did some practice problems with that. So what your problem says, we're going to be looking at exercise 1, is it says order the following bonds according to the polarity. So we've got HH, and we're looking at OH. We're looking at CLH. We're looking at SH and FH. So if we want to know which one of these is polar, which one is the least polar, which is the most polar, we need to kind of look at, okay, let's look at this being the nonpolar end and this being the polar end. The only way that I can organize these is to know the difference between the electronegativity difference between these. So obviously this one's easy. It's 0, no matter what. It's the same element. So if you look at OH, I don't know the values of O. If I flip back over on my notes, I think O is 3.5 and H is 2.1. So the difference between those two is going to be 1.4. And then I know hydrogen is 2.1, chlorine is 3. So that would be a difference of 0.9. That's supposed to be a 9. And then S and H, well, H is 2.1, S is 2.5, so that's just a difference of 0.4. And then I know fluorine is 4, and then hydrogen is 2.1, so that's a huge difference of 1.9. So if I look on the nonpolar side, nonpolar, remember, is anything less than 0.4. So my most nonpolar one would be the HH bond. So that one's going to be less than, and I'm going to kind of mark them out as I go. HH would be less than, the next one that's the smallest is SH. And then that one would be less than OH. And then that would be, oh, I messed up. Nope. So it's not OH first. After SH would be CLH, because it's 0.9. And then that one would be less than OH, which would be less than, the most polar one is FH, because it has the highest electronegativity difference. So there are the answers for that problem. Before I kind of move on, I just want you to understand I'm kind of moving and teaching these all in kind of different sections here, but 8.3 is the next section that's covered. I'm going to cover that at the end of the chapter. 8.4, we're going to kind of review right now. 8.5 and 8.6, we're not actually going to even cover at all in this chapter. So right now, we're going to look at 8.4 and just kind of review. This is stuff that kind of was talked about last chapter. So I need you to understand that if you've got a calcium ion, so calcium ion is 2+, that means it's lost 2 electrons. I need you to understand how to write these electron configurations. So what you need to think about here is, first off, what is the electron configuration of calcium atom? So that would be 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. But that 2+ over here means it's lost 2 electrons. So you have to be able to think this through and say, where would it be losing those 2 electrons? Well, they're going to be losing that 4s orbital. So if you're looking for the answer, you actually are looking for the electron configuration of argon, which is also the electron configuration of the calcium ion. So that's kind of how that you have to make sure you read those questions carefully. Are they asking about the electron configuration for an atom or an ion? So on the flip side, if you've got it, that's a cation. If you've got an anion, oh, and what you also need to be able to do is understand that if this is the calcium atom, that the ion actually becomes smaller than the original atom. And I did talk about that last chapter. So then the next one we're going to look at, say you're looking at the oxide ion. So it's O2-. Well, if I just think about what is the electron configuration of oxygen, I know it's 1s2, 2s2, and 2p4. But that 2- means it's going to gain 2 electrons. So, and it's going to gain 2 electrons in this orbital right here, and you would be looking for that electron configuration, which is actually the electron configuration of neon. So just make sure you kind of understand that. And again, if this is an oxygen atom, the ion actually gets bigger, the anion does, because it's now gained 2 electrons. So cations are the ones that shrink, and then anions are the ones that expand and get bigger. So the last thing we're going to kind of look at is being able to arrange things in sizes based on their cation or anion state. So we're going to be looking at arranging these sizes of strontium ion. We're going to be looking at the bromide ion. We're going to be looking at the selenium ion. And we're going to be looking at the rubidium ion. So what I want you to do is just take a look at the location of these elements on the periodic table. So I'm going to get my periodic table in front of me, and if you kind of take a look at this, strontium and rubidium are right next to each other on the periodic table. So strontium is just to the right of it. So technically, by trend, strontium should be smaller than rubidium. And strontium is going to definitely be smaller than it because it's losing 2 electrons versus rubidium losing 1. But then the other 2, the bromide ion and the selenium ion, they're actually in the row before it. So really they should be smaller, but what you have to understand here is that those ions are actually gaining electrons. Those are becoming anions, and they're getting a lot bigger. So if I'm arranging these from size, I'm going to go from largest on this side to smallest on this side. So the largest ion here is that selenium ion. So that's going to be your largest atom. Technically it is in the row before it, but what you have to understand is because it's gaining electrons, it is getting much bigger than those other atoms. So selenium is the largest one. So it's greater than, the next up is the bromide ion. And then that one is going to be greater than, and we kind of talked about this, rubidium would be bigger than the strontium ion. So the strontium ion is going to be the smallest one out of all of those anions, or out of all those ions, not just specifically anions. Okay, I'm just going to quickly go through this page because this is just kind of the introduction, just kind of the overview of what you're going to be doing. I can tell you this, there's not really anything that I'm going to talk about down at the bottom. We will get into that when we actually get into drawing Lewis structures. So what I really want you to get out of this is these numbered. I'm going to teach you in this chapter how to draw Lewis structures. You learned last year, you learned some really easy ones. We're going to get into some more in-depth ones for this chapter. And then we're going to kind of see what happens to the actual shape, how those electrons being placed around those structures changes the geometry of it. It's called the VSEPR theory. That stands for valence shell electron pair repulsion. So we'll look at that later. And then number 3 there, we're just going to briefly touch on something in chapter 9 called hybridization. So I'm going to teach you, it's actually really easy. I'm just going to teach you the hybridization of a central atom. So I'll teach you that later as we kind of talk about how the structures go together. So I'll kind of touch on it here. You probably have understanding that you can have a single bond. So a single bond would just be when I have 2 electrons and they're sharing their electrons. And I can't connect those perfectly. That would be considered a sigma bond when it's a single bond. And then when I have a double bond, what happens is I've got actually 2 sets of electrons that are going to share electrons. So and then there's also, I'm going to draw this one over to this side, there is also triple bonds where you actually have 3 sets of electrons sharing. So some elements, and they specifically tell you up here, carbon, nitrogen, I just marked it out. So if you kind of think of CNOPs, so carbon, nitrogen, oxygen, phosphorus, and sulfur atoms are notorious for being in multiple bonds, meaning either in single or in double or triple bonds. So if it's a single bond, it's considered to be sigma. If it's a double or a triple, what they have is they have 1 sigma bond and then they have what's called a pi bond. I don't need you to understand a lot about that. I just need you to understand that 1, pi bonds are extremely weak. It says pi bonds are weaker than sigma and they're never alone. So if you at least have a single bond, it's considered to be a sigma bond. Anything beyond that is a pi bond. 1 is kind of weaker than the other. That's all I really need you to know about that. Now, in this blank spot below there, I'm going to change my colors. If you have multiple bonds, what it does is it actually changes the bond length, and it talks about it here. The bond length is shorter for double and triple. So it's almost like the more electrons that are being shared between two elements, it kind of shrinks the bond length down. So if I have a single bond, it's going to be more like, it'll be a longer bond. But if it's a double bond, those atoms are going to be a little bit closer together, and that bond length will be shorter. And then if I have a triple bond, they're going to be even shorter. So the distance between those two atoms is even shorter. That's what bond length is called. So they talk about it a little bit more on the next page, and that's where I'm going to kind of go into it a little bit more, but it's introduced here. So I'm going to go ahead and skip to the next page. So go ahead and turn your page. So here's your next page in your note. They talk about not just bond length, but they talk about something called bond order. So bond order is, if it's just a single bond, then it's got a bond order of 1. If it's got two pairs, meaning if it's a double bond, then it has a bond order of 2. If it has a triple bond, then it's considered to be bond order 3. You don't really need to understand any of that, but this would just be, again, single bond versus double bond versus triple bond and what their bond order is. That's pretty straightforward. And again, the bond length, it's going to be based on the distance between the nucleus of those two bonded atoms. So you kind of if you compare these, if you have a single bond, it would be 143. When you throw in a double bond, it knocks that bond length down, and if you have a triple bond, it knocks it down even more. So bond energy, the definition here says the greater number of electron pairs between atoms, the shorter the bond will be. And there's this box right here, that table. You can kind of compare some of those and just look at the distances between what's going on when they have multiple bonds in there. That's all I really need you to understand about that. So at the very bottom here, what you have to understand is, and we're going to kind of be reviewing thermochemistry here. So that was back in chapter 6. You use something called table values. I don't know if you remember the table value method to actually answer questions about delta H. So you use something called standard enthalpy of formations. So you use some values from an index in the book to look up some values, and what you did was you always took products and you subtracted them from reactants. So this is going to be something that looks similar, but it's a completely separate concept. So in this case, what we're going to be looking at is not the standard enthalpies of formations. We're going to be looking at the bond energy between different bonds that are either breaking or forming to cause this chemical reaction to happen, and whether it's endothermic or exothermic. So I think of it like this. I think of my bonds broken minus my bonds formed. My bonds broken are always going to be my reactants, because those are the bonds that would be breaking. The ones that are formed are always going to be my products. So in this case, you're going to be doing it backwards than what you're used to. You're going to be taking reactants minus products. So kind of keep that in mind. So I'm going to flip to the next page so you can see the table that we're working with. So again, there's a very important note up here, and it's kind of what I talked to you about. This is backwards from the thermodynamics, the big mama equation that we always used for this. So this is always a misconception, and some students get really tripped up by it, but that's why it's in 2 separate chapters. So this one is covered in chapter 8, and it's talking about, if you look, these are bond energies. Those are not standard enthalpies of formations. Those are not delta H values. This is the amount of energy that it takes to break a certain bond. And if you can tell, if you look at my problem, it does not match yours. So I'm going to flip to a new page, and we're going to actually work it on there, because this is just gibberish. I'm not really sure why it came over like this. But you're looking at exercise 5 in your notes, and I'm going to kind of walk you through that. So let me add a page on mine. Here's a blank page that we're going to kind of work. So you've got this chemical formula. You've got CH4 plus 2Cl2 plus 2F2 going to CF2Cl2 plus 2HF plus 2HCl. So there's your chemical formula, and what they want to do is they want you to find the enthalpy, but you're going to be finding the enthalpy of this reaction based on what's going on with the different bonds breaking. So to really do this, we have to, again, these are going to be your broken over here. These are going to be your formed over here. So I'm going to focus on my broken first. So what I have to do to kind of understand this is when I look at CH4, I need to be thinking that means I've got a carbon attached to 4 hydrogen. So I'm not just breaking one carbon-hydrogen bond, I'm breaking 4 of them. So if you look at that average bond energies in your notes, that table 8.4, to break a carbon-hydrogen bond, it takes 413 kilojoules of energy. So I'm going to have to, if I'm talking about my broken, I'm going to have to say 4 times 413. That's just for the CH4. Now, the next one I need to look at is the 2Cl2. Okay, so the way I think about this is I've got a chlorine bonded with a chlorine, but I've got 2 of them. So I got chlorine, chlorine. So if I look up above and say, okay, how much energy does it take to break a bond between 2 chlorine atoms? If you look at that value in that table, it's 239. So here I'm going to have to say 2 times 239. And then again, my next one, I'm looking at F2, 2F2. So that means I have an F bonded with an F, and I have another F bonded with an F, which is not writing it. Okay, so up above, if I look at fluorine, how much energy does it take to break a fluorine bond? It's 154. So I'm going to have 2 times 154. So that is going to be the total energy of my bonds broken. Now I'm going to have to look at saying broken. It's always broken minus form. So I'm going to say this is going to be minus, and then I've got to figure out all my information for my product side, my form side. So the CF2Cl2. So if carbon's in a bond, you're going to find when we start drawing structures. This will make more sense once we draw structures. I've got a carbon atom in the middle. I've got 2 fluorine, and I've got 2 chlorine. So I got a fluorine here, chlorine here, chlorine here, chlorine here. So if I think about what bonds are going to be breaking, I'm going to have 2 carbon-fluorine bonds break. So the bond between carbon and fluorine is 485. So there's 2 of them, though. So I'm going to say 2 times 485. And then I'm going to be adding that with the 2 chlorines. And that's going to be 2 times 339. So then next up, I've got 2HF. That means I've got an H bonded with an F, and I've got another H bonded with an F. So if you look at that one, it's going to be, I think the value is 565. So I'm going to say this is 2 times 565. And then I've got my last one, I've got 2HCl. That means I've got an HCl and an HCl bonded. So if I look at that one, I think it's 400, the value is 427. So I'm kind of running out of room. I'm going to say 2 times 427. That's all of my formed. So now I need to go through and do all my math. So I'm going to say over here, I'm going to start over here all the way on the left. 4 times 413 is 1652. And I'm going to add that with 2 times 239, which is 478. And I'm going to add that with 2 times 154, which is 308. So that's all my broken. And then I'm going to figure out all of my formed. So 2 times 485, 970, plus 2 times 339 is 678. 2 times 565 is 1,130. And then the 2 times 427 is 854. So there's all my values. So again, I'm going to have to add up all of these and subtract them from all of these. So 1652 plus 478 plus 308 is 2,438. That's an 8. Minus, then I'm going to add 970, 678, 1130, and 854. I get 36, 32. So then I just need to subtract those 2 values. It's not biggest minus smallest. I've got to always take broken minus formed. So this is why I get a negative value here. And if you remember from thermochemistry, if it's a negative value, this means this is an exothermic reaction and it gives off heat as it goes through this reaction. So that's all the basics to bonding. I'm going to have some separate videos again some separate notes for the rest of this chapter. You can refer to the rest of the notes in this chapter, but I'm going to break it down and just give you straight exactly what you need to know to get through this chapter. So that's all I have for now. I'll come up with some practice videos, and I'll have an assignment over this information. Let me know if you need help with anything.